All right, here we are at Troy Howard Middle School. Thought you guys would like to do a tech ed enrichment on electricity, just some basic electrical theory stuff. I'm going to show you some just little experiments, and hopefully this will be part of a series. Maybe next week we'll do something to do with electric motors and electric magnetism. I don't know how long it's going to be, probably about half an hour, and I'll put it right on my classroom. But I don't know if you guys have done anything with basic electricity, but it all comes down to an atom, right? You've got an atom here, a diagram of an atom. The middle of it is called the nucleus, and then rotating or orbiting actually around the outside of the nucleus, you have tiny particles called electrons. And within the nucleus, you have little positively charged protons, okay? So if you have one proton here, one electron here, that atom is neutral, it doesn't have any charge. But you can take an atom, and if you add, like this one here, if you add an additional electron, okay, so now you have two electrons, one proton, then it becomes a charged particle, it becomes a negative charge because electrons are charged negative, right? So if you have this situation where you have electrons, more electrons in this atom here, and maybe neutral, or you add another proton again, take away an electron actually, and then you have two protons, and you have a positively charged ion and a negatively charged ion. So according to the law of charges, unlike charges want to go attract to each other. Minus wants to go to plus all the time, right? So if you create a path for that to happen, this extra electron wants to go in and fill this void over here. So you create a path, and you get a flow of electrons, and that's what electricity is. That's where the word electricity comes from, electrons. So electricity is basically a flow of electrons. Okay? And the way you get it to flow is you just need to, something like a battery here. This little diagram of a 9-volt battery. If you have material that built up negatively charged ions here and positively charged ones here, you can see the symbols on the top there. If you then allow a path for that to flow, then you get the flow of electricity. And that's real simple, basic definition of electricity. So it's a flow of electrons, and it flows about the same rate as light, which is, hold on just a second here, I'm going to put it down here. Electricity flows at 186,000 miles per second, same speed as light. Okay. So what does electricity flow through? It flows through things that are good conductors. Conductors have a lot of electrons that are not firmly attached to the nucleus. They're free-flowing, and they allow those electrons to flow. So examples of good conducting materials, mostly metals. Pretty much all metals conduct. And some of them have a little meter here. It's called a multimeter. I'm going to be using it for a couple different things. Right now I'm going to use it to check to see what's a good conductor. What it has inside here is got a battery, a little 9-volt battery in there. And when I put it on, it's called an ohm meter. It measures resistance. It puts a little electrical charge out through those two leads there. So what I can do with that is I can check to see if electricity flows. I know that electricity will flow from this to that. So I'm getting a 0.0 reading. Zero. Yeah. So what that means is there's no resistance. Electricity is going through, no problem. If I get that reading, which means there's no electricity, or if I get any other number reading, that means electricity is getting slowed down a little bit. So if you take something that we know is a good conductor, we recognize that. Material is copper, which is used for wire. Most wire inside your house is copper. We can check that and see how that conducts, and we can see we're getting 0, which means it's no resistance to the flow of electricity. It's conducting really well. If you take something like rubber, it's a piece of old rubber inner tube, and we try to conduct electricity through that, we don't get any reading on that. So we know that's a good insulator. So we got conductors, it's a good conductor, it's a good insulator. So some other materials, we said that copper is a good conductor. The best conductor, copper is the 4th best. The best conductor is silver, and then there's gold. Actually, I think copper's 3rd. And then there's aluminum as well. So gold, silver, copper, and aluminum. Here's a piece of gold, not really solid gold, but audio connections, a lot of times they use gold plate, and it makes good contact, and just like any other thing. But what the advantage of gold is, it doesn't oxidize. You can take a piece of gold, throw it in the ground, dig it up in 1,000 years, it'll still be bright and shiny. That's why it's so valuable. But if you use it as a plating, you're not going to get oxides or corrosion on it, which could make, which could make it reduce your resistance. I'm moving it around a little bit here. So we're getting good conductivity. So what I did with this piece of wire, you see this wire, heavy piece of copper stranded wire. On the outside, that coating is called insulation. So you got the conducting wire inside, and then you got insulation, which is made out of plastic on the outside. So if I put my leads, one on each end of that, so I'm getting conductivity through that wire. And that's a good way to check a wire, to see if there's a break in it from getting electricity through it. You just send a little electricity through it and see what you get. If I put it on the outside, the insulation part, I'm getting nothing. So that's my insulator. Here's just another piece of wire. By the way, the color coding on wire, for the most part, black represents negative and red represents positive. So those are the two charges with electricity. So just another example here, this little thing, I forgot to show you that when I was talking about charged ions. But so if you have ions that are charged, the same charge, they repel each other. So if you have a plus and minus, they go together. Minus and minus, they repel each other. And you can see that with this example here. This is an electroscope, and there's a conducting material down through, and on the bottom, hanging on the bottom, is two really thin pieces of aluminum foil, which are really good conductors. But what I'm going to do is I'm going to demonstrate static electricity. Static electricity, you probably walked across a rug or something like that, and scrape your feet, and you touch something metal or something that conducts, you get a shock. And that what's happening when you walk across the rug is you're stripping electrons off that rug, and they're building up on you. And then they build up enough to a point where you get close to something or touch something, they'll discharge. It's the same way lightning works. Lightning is just basically a bunch of electrons building up in a cloud. So it gets to the point where it discharges through the air because of the moisture in the air into the ground. But with this, I'm going to simulate that. I'm just going to take a good insulating material, and I'm stripping the electrons off of this cloth, and they're building up on that rod. And you can see the two foil pieces. See how they separate? You get that, Dan? You see them, the two foils separating. You may be able to see it better when you look at it on your bigger screens, but you separate like that. On a moist day like this, you don't get static electricity as well, because the electrons, they tend to neutralize out through the moisture in the air. Dry days, it works a lot better. You probably notice that in the wintertime, you get more shocks. All right. So these over here, these are insulators. You probably recognize these. These are used on telephone poles. When you run power from pole to pole, if you connect it directly to that wooden pole, with that amount of voltage, it's going to conduct down to the ground, and it's going to be a big problem, right? So these insulators are what attaches the wire, basically, or it's the barrier between the wire and the pole. They're made out of ceramic. So ceramic would be clay and glass, brick, stone, cement, all that is considered ceramic. So these are the modern ones that they use, and these are some of the older style ones that you may have seen, glass, just a smaller version. Because now we have a lot more voltage. The wires that go from pole to pole, those are about 10,000 volts in those wires, a lot of current. Compared to what's in your house walls, it's about 120. And those wires are not copper. Those are made out of aluminum. It would be really expensive to run copper, big copper cable all over the place. It's heavy too, so aluminum works better there, but it doesn't work as well inside the house. All right, so you got your conductors, insulators, water. A lot of people ask about water. Water does conduct, only if it's enough voltage. It doesn't guarantee there's going to be good conductivity through water unless there's a lot of it. And that's why you have to be careful. So it's a little unpredictable that way. All right, so we got resistance is the next thing. So we saw that we were getting zero resistance on here, meaning there was good conductivity. Resistance is sometimes something that slows down the flow of electricity. When you're trying to force electricity through a conductor, and maybe the conductor is a little too small, that conductor, basically the electrons rub against each other and they create friction, and friction creates heat. So when you get electrical heat is from resistance or electrical friction. And that's beneficial. You can use that. You can use that to convert electrical energy into heat and even light. And you can see that here with this little, you guys recognize, little 9-volt battery. There's 9 volts right there. There's a plus, there's a minus side. And there's a fair amount of voltage in here. So if I take a piece of steel wool, stuff that you use for abrasive material, and I connect it on there, can you see that? You see how you're getting light, you're getting some heat, enough to burn that steel wool. Okay, that's a good example of electrical resistance. So it's kind of like if you look at your toaster in your kitchen, you see those glowing wires, you're forcing electricity through a conductor that's not really a good conductor, and so it heats up just like that. The reason this one heated up is because the wires are so small, the electricity's just having a hard time getting through there, creating a lot of resistance. That's why you have to be careful with 9 volts. If you take them and put them, since the two connections are close to each other, you can get that same kind of short circuit in your pocket with change, or putting them in a metal container, or with other batteries and things like that. You got to be careful with those. Round batteries, you don't have to worry as much because the ends are so far apart. They're not going to end up shorting each other. But some other things besides a toaster, anything that creates heat with electricity, a hot water heater, the list goes on and on. But also light, not so much anymore, because we don't use resistance for creating light. But Thomas Edison invented the light bulb, and it's basically a little element that glows because the resistance is high, and it creates that heat and that light. And that's how a light bulb, an incandescent light bulb works. And you can see that one. Can you see that element dangling around in there? If you can see it. And then this one here is a much older one. The reason for the bulb on the outside is a couple of reasons. Well, it keeps you from conducting electricity to the element there, but also it's a vacuum. If you take the air out, it's not going to burn. You're not going to get the element burning out if there's no air, right? We learned that in class, probably when we did rockets, how you have to have oxygen to burn something. So inside the bulb is a vacuum. We call them vacuum tubes. All right, so that's resistance. All right, so how do you measure electricity? Probably I've used the term already, voltage. There's voltage, there's amperage, and resistance. Voltage is kind of like your supply of electricity. Like in this battery, I've got 9 volts. Okay, that's how much electricity I have from my supply. How much I let out at a time and how fast it comes out, that's your current. So a good way to understand that is to look at water. So if you have a tank of water like this, you have a certain amount of water in that tank. That's your supply, that's your voltage. Okay, it's static, it's not moving anywhere, just like in the battery, until you allow it to flow out. That's when you get your flow of electricity, and that's when you get your work out of electricity. So that flow, the rate of that flow, the current, like water, right, has current in the river, the rate of that flow is amperage or current. They're almost interchangeable, those two words. So if I open the valve just a little bit of current, I'm not going to get as much energy from that electricity, but if I open the valve all the way and it comes shooting out really fast, I can get a lot of work done with that amount of electricity. So that's how we're able to power different things, with different appliances, different things that we use every day. It's basically the rate of current that changes how much work you get out of electricity. Am I making sense, Dan? Okay. So to show different amounts of voltage, I'm going to show you some different batteries over here. Different amounts of voltage. So batteries are DC current. Okay. So what I'm going to do with this little meter, I'm going to put it on the voltage. I can measure voltage with this as well, and I can check and see how many volts there are. We know in our 9 volt we had 9. So when I set this up, we should be able to get a reading of 9 out of that. Put the 2 leads on there. And we're getting, it's a little low, 8.77. So pretty close to 9, but not quite. And then round batteries. So we got this big, what is this, a D battery? We got both ends, one's minus, one's plus, and we're getting 1.5. And that's pretty much what this should be, 1.5. 1.5, it says it on there somewhere. Smaller one, the AAA, also 1.5. So round batteries are pretty much, are all the same voltage. So this is a C battery. The difference between the size is how many stored particles there are in there. So a D battery is going to give you the same voltage as a AAA battery, but this is going to last long before it starts to run out of that energy. You have more of those particles in there, it'll last a long time. 9-volt battery gives out a lot more. So there's quite a difference, 1.5 volts to 9 volts. So this battery here is a, let me turn that back up a little bit. No, that's probably better. So this battery here is a car battery like you have in a car or something like that. And this is also a DC current, which I don't want to get into right now. But this is the plus side, this is the minus side. So if I put my meter on the inside, just put my meter on that, it should be, if we do this right, we should get 12. So the 12, all cars and boats and motorcycles, I think, I'm not sure about snowmobiles, they might be 6 volt, but these are all 12 volt systems. You get 12 volts of electricity, so I can see this battery is pretty well charged. This is a wet cell battery, which means there's liquid in here, there's acid in here. These are dry cell batteries that have like a pasty, almost dry material in there that make up the electrolyte. Aside. So how much is flowing through this? And that's where you got to be careful. I wouldn't do anything like this at home, but I got to change it first of all to AC, which is alternating current, and I got to put it on the right voltage a little bit higher, so I don't ruin my meter. I've got it set a little bit higher. Now if I take my reads carefully so I don't touch any metal while I do this, I stick that in there, and then I stick this one on this side. I get about 100. It's supposed to be about 120. But in any building, you're going to have variances. You're going to have up and down. This is 122.7. So that's why it's important with electronics that have require a certain amount of current or voltage that you run it through a spike bar, because you can get up and down spikes and drops in that voltage. So those are you see how I connected that in plus and minus. That third one, that third prong there, doesn't do anything. That's a ground. That's for safety. So, using an appliance or using a power tool or something, if the electricity, if something inside tries to ground to the outside of it, it'll pick up that and will take it safely out to ground it to a ground rod somewhere, not through you. But anyway, so let's see here. Let's move the meter for a minute. So circuits, let me use this little thing here. This is just a DC power supply. This is basically just like the battery. And what I can do with this is I can put out voltage right here, put out like 2 right now. I can turn it all the way up to, I guess it goes all the way up to 17 volts. And then I can also change the current. Right now I've got that turned up all the way because we just want to let out as much as we want to. We're going to regulate that with the voltage meter here, the voltage die here. But so in order for electricity to flow, you need to have something called a circuit. So a circuit is a path for the electricity to flow. Okay, I've got my positive lead connected to this wire, which is going to go through this light bulb. But right now I'm not getting any light because it's an incomplete circuit. It has to be a continuous path back to the source. So from the minus side to the plus side, it's the electrons, they want to go together. So we need to create a conducting path for that to happen. So when I hook this up, turn that down a little bit, and I turn up my supply there, I get light, okay? And I can adjust that light here. Let's put it at, let's leave it right there, about 3 volts or so. If we want to control that, we can add a switch. This is just a single pole switch. And all the switches, just like a light switch, is a way to control the circuit by interrupting the circuit. So with a switch like this, there's just a mechanical switch. It It just provides a way to either open the circuit. Right now, there's no way for the electricity to get through that. When I flip this lever over, now I've completed that path. The current goes back, and so I can control my light. That's how a simple switch works. This is considered just a series circuit. So if I want to add another light to the circuit, let's turn it up a little bit. Otherwise we're going to lose it. Let's go up to like 4 volts maybe. 5, let's go to 5. All right, so is that about 5 or so? So if we want to connect another light in here, see how bright that is, right? I want to connect another light in here. We can do that by just continuing the path, but adding another light to the system. Let's turn the switch off. And now, when I turn this on, both are lit, but you probably notice that they're both much dimmer. Because what we did when we add the other light in this type of circuit, a series circuit, that voltage is being divided between the two. Okay, so going back to this one here, you can see how bright that is, and it's drawing 30, what does it say? 31? 31 amps. But when I connect it here, each light is getting only 2 amps. So that's a series circuit. I can add another one now. We'll see what happens. Just take that out. Connect on the light here. Got barely enough light, and now we're dividing that voltage up three ways. Okay, so we're getting much less. So that's one of the issues with series circuits like that. But they can be useful because if you want to divide, if that's what you want, that's what you're looking for, less energy in each bulb, you can divide it up that way. But the problem with this type of circuit is if one of these bulbs burns out, the other two go out because I've broken that path, and everything in that path is now not going to have electricity flowing through it. So that's a series circuit. So it's another type of circuit where you can actually have a parallel circuit. We'll take the switch down just to simplify, where you can actually have an alternate path for the current to flow through. So you know, if one bulb burns out, we don't have to worry about it. This one's called a parallel circuit. So we'll start with just one here. Actually, let's just do it this way. Start with just one light. Go back to our bright light. Got that bright light on there. And then if I want to add another light like I did with the series, I have to connect 2 wires to each one. So now I've got two. I haven't changed my voltage, but I'm still getting good brightness. It's been drawing more amperage that way. We're drawing more current. We were just putting out, what, 31, now we're putting out 62 or something like that, 63. So with this kind of circuit, the current path has 2 ways. It can go this way, or it can go that way. So if this bulb burns out, it doesn't affect the other one because it's an alternate path for it. And it didn't change, it just drew more current. It didn't change how much those lights burned, how much energy I'm getting. So if I add another one in there, the third one, you should get equal light from that one. So that's a parallel. They call it parallel because they're kind of set up in parallel. Now we're drawing, what, 93 amps there. I think that's right. All right, so that's a basic circuit. We'll shut that off for a minute. Actually, let's leave it on. So anything that you guys, we use these in class. We know how to hook these up. These are electric motors. And we can connect that, I suppose, in series here as well. We can do this now. I'm getting good. I'm actually pulling out 1.7 something amps now. All right. So some other, just as another example of a circuit, this is an electronic circuit. This is a different type of light. These are incandescent. They use the resistance like a Edison light bulb, but this one is an LED light emitting diode. There is no conducting wire in that bulb. It works differently. There's almost like a fluorescent light. There's no element in it. Let me see if I can get this thing to work. And you see that LED light lit there. LEDs are normally, you wouldn't be able to put 9 volts into them because they would burn out. They don't, they can't take that much electricity. So that's why in this circuit, and you see these in a lot of electronic circuits, you have these little resistors in there. They slow it down. They create resistance to slow it down when you want to protect something or adjust it. This thing here is called a capacitor. Kind of like a battery. It stores electricity so that if you want to have a constant supply of electricity, that actually gives back energy. So can you see that okay? So if I take this battery out, you can see that light stays lit until it slowly drains out. So if I've got like variances in my current supply, my electrical supply, that kind of fills in the void, so it makes a steady flow of electricity. So a lot of logic circuits and things like that need that precise amount of electrical current. Capacitors can provide that. They can absorb and give back energy, but that does store enough energy. Bigger capacitors actually store enough energy that they can store for a long period and get a shock off it, but something this small is not going to do that. You can see it'll fade away. All right. I think that covers it. I think next time we do a little lesson like this, I'll do something on electromagnetism and motors and how you guys build a project with electric motor. A few ideas. So look for it on my classroom.